morning to all of you once again. So today we will take up something which is known as CMOS inverter static characteristics. Okay, static means today we are going to analyze what happens to an inverter for various DC operating conditions. We are not going to speak about delay or transient conditions, which we will be discussing in detail in the next class. Okay. If you see here, now before we talk about the inverter characteristics, there is an for an DC point of view, there is one important figure of merit which is known as noise margin. Okay, so let me increase the size of the mouse also. Yeah. Which is known as the noise margin. Okay, so this is known as the VTC curve. Okay, VTC curve is like on the x-axis you have the input voltage, and on the y-axis you have the output voltage, right? So initially when the input is 0, the output is in this case it is shown as an VDD, like because it is an CMOS. But not necessarily, it need not be VDD, it can be less than that also. Okay, so that would be known as VOH. Okay, so for CMOS it is VDD, but for other configurations we saw for the BJT based circuits, the output may not be VOH, right? So in those cases it VOH. Okay, it is a most generalized expression. So VDD, you have VDD. And then as you keep increasing the input voltage, there would come a state where the nMOS will be switched on, and so subsequently the voltage will fall, and then it would come towards the 0, right? Here also this graph belongs to specifically to an CMOS, where you have an PMOS and an nMOS, and hence VOH is VDD and VOL. Okay, V output for low conditions, V output for high conditions. Okay, so these are the two voltages, which is 0 and VDD for an CMOS. Okay, so this is how the graph looks like. Okay, now there are a few other things. This is the place where the slope of this curve is -1, and here also the slope of the curve is -1. And if you from that point, if you drop a straight line, we hit a point which is known as VIL. VIL is V input low. Okay, so from here to here, okay, the input will be considered as 1. Okay, within this whatever, if the input is here, the output will be from here to here. Okay, so you can say that the next stage would consider from here to here as 1. Okay, so that is the reason 0 to VIL. It will be generally termed as as the input noise margin. Okay, so this margin, so this inverter can tolerate this much of noise, and hence it is known as input noise margin. Okay, NML. Okay, so noise margin low. Similarly, once it goes high, I have this point at which the slope is again -1. This is known as VIH. And from VDD to VIH, this is known as noise margin high. So any voltage within this range will be considered as a high input, as an input corresponding to high, right? So that is the reason this much of any noise. Okay, it has to be high normally, but a noise which can bring down the signal maximum up to VIH is permissible. Okay, this can handle that much of noise, and hence this is known as noise margin high. Similarly, the input is ideally should be 0, but if because of noise it can come up to VIL. Okay, so that is the reason we call it as noise margin. So greater the VIL and VIH, so that much will be the that much better for us, right? So it can tolerate that much of noise. Okay, ideally if it is this curve should what should be the ideal curve? It could go straight here, and at VDD by 2 it should fall down, and it should go like this. Okay, in that case that will be the noise margin, VDD by 2. Okay, so we have another definition which is known as an inverter threshold, that is somewhere in between. Okay, so we can consider that inverter is switching from 0 to 1 at this point. Okay, we'll make a more better explanation of a VM subsequently in one of our slides. Okay, so is this concept of noise margin understood to everybody? Okay, can I have some response?
Yes, sir.
Yeah. Okay.
Sir.
Yeah. Tell me. Yeah. Okay.
Sir, if you are applying some noise at the gate,
Yeah.
and such that noise is greater than Vth, then due to GM, transconductance, we will expect the current IDS flowing.
Yes.
So is there a relationship between the noise and Vth? The threshold of the gate of the MOSFET?
Yeah, it will be. There will be threshold and the relative strength of the right, and we will derive these equations of the noise margin today. Okay, so we'll see it is a factor. The greater the threshold voltage, that much would be the better. Okay, so we'll derive those expressions today. Okay, earlier days this was not that much in focus, but now with technology scaling, the power supply voltage itself is very low, right? And hence these everything has become prone to noise. So noise margins have become very critical now, right? So if it is say earlier 3 volt or 1.8 volt, so this would be close to 1.2 or 1.5 volt. So it doesn't matter, like you don't have noise coming off that order. Now we are speaking about for 7 nanometer, I guess the power supply voltage is less than 1, right? It is around 0.8 volt or something. Now you can imagine the entire curve has shrunk. Okay, both in the y and the x axis, and you just have close to 0.3, 0.4 volt as the noise margins. Okay, so those are the issues which come up in circuits, modern day circuits. So you have schematic triggers and all, where you have an hysteresis curve. For the positive going, you push it towards the right, and for the negative coming VDD, you push it towards the left. So that aspect will be covered in your advanced VLSI classes. Okay, so time being, we have a single curve, and we have defined noise margin, and we'll move ahead and see how things look like. Okay, so the simplest inverter initially, which was, yeah, tell me.
In the previous curve where you had point B and C, they are marked as VDD by 2 plus VT and VDD by 2 minus VT.
Yeah.
So this VDD by 2 plus VT is for PMOS and minus VT is for nMOS, right? Or
yes, correct. This is it is negative for PMOS, and hence it is VT is negative for PMOS, and that is why it's written as plus VT. Okay. So let's see the first and foremost topology which we are going to see is a simple nMOS and a resistor based circuit. Okay, so what is done is you have an nMOS and you have a load resistance. So initially, if the gate voltage is 0, this is switched off, and you can expect a full voltage to be available here. When nMOS is switched on, you will have some current flowing, and you can have an ID RL drop, so hence the voltage comes down. Whether it will come to 0 or not, let's see. Okay, so this is the output characteristics. You have a VD. So this is VD and this is ID. This is for various VGS. Okay, so this is known as load line. Okay, what is load line? This is the these curves represents the characteristics of the N MOSFETs, and this straight line represents the load line. Okay, what is load line is like from here. If what if RL is for VDD, this output to be 0. Okay, what would be the this the for output to be 0. Okay, maximum current has to flow here, which will be VDD divided by RL. So I mark this point, and for the output to be full VDD, ID has to be 0. That is the maximum. So this is the operating line of the resistor with a slope of 1 by RL. So this is load line with respect to this resistor, which is just following the Ohm's law. So is it understood how this line has been drawn? These two lines, all of you?
Yes, sir. Can we use a PMOS in place of RL?
Yeah, we will be doing that. We'll do that analysis. Okay. So we start with RL and we'll see other topologies. Okay. Now, if you see here, so how to find out the output VTC curve? So obviously when V in, okay, V in is 0, right? So this is the curve which is at the bottom most, okay, which is running close to the x-axis. It is intercepting this vertical line, and hence you get a full VDD. Okay, when I apply VDD out here, right? So this is the curve which is going the topmost, and a VGS curve. This is intercepting this particular line out here, right? So it is so this is the point out here. So that doesn't correspond to VDD, but it will be slightly less than VDD, and hence you will find you don't have a perfect 0 out here, right? Okay, so you have this curve coming like this. So when I am using an RL resistance, I don't have a VTC curve as I have observed for an CMOS. This would be the when I am using an PMOS, this is the kind of curve which is expected, or an ideal inverter should have these kind of curves. But when I am using a resistance, so this is the kind of curve which I will get. Okay, so this is for VGS is equal to 0. This is VGS is equal to 1. So this is so you see it is intercepting the load line at this particular point. So if I draw an horizontal line here, so it will not touch a VDD. So I have some VOL is not 0, but it will be slightly higher. Sorry. From there I have to bring an line towards the x-axis. So that will give me a VOL, right? So this point here VOL. So this much residual voltage is available out here. So that will get as a VOL. So this is how there is an issue with this transistor. Is it okay? Correct? So it is understood otherwise also. If I talk about like some ID current has to flow, right? So the entire ID cannot flow. ID equal to VDD by RL cannot flow here. That will bring VDS equal to 0 in this particular case, right? So that condition cannot be met. Both the conditions cannot be met, and the current of this is defined by this particular equation. So I cannot have current beyond that ID equation. Okay. Now seeing this graph, can anybody say how to reduce VOL further to bring it as close to 0? What can be done? Anybody? It's simple.
By changing RL, you can control the slope of the load line.
Yeah.
Sparing the
One like rightly brought out. If you can be more specific, if I increase RL, will it come to 0? Close to 0?
yes, sir. VDD minus IDRL. So RL increase,
Okay.
so will come down.
So what happens to this curve? If I increase RL, this will come slightly lower, right? Let me take
Correct,
a
sir.
pointer.
Slope.
Okay.
Slope will be
So if I
less.
increase RL, this will be the line, right?
Open.
So now I will have this. It is coming to close to VOL. Okay. So there is one option. So can you see some disadvantage in increasing RL?
The steepness of the curve will go less. It will be less steep, and
Driving
noise
capability
margin
decrease
will be
will
less.
ID
I
decreases.
think if you increase the RL, it will come something like this. So steepness would be better. But suppose I have a capacitor like this, right? Next stage, that needs to be charged like this, right? So my it will increase my delay. Is it okay?
It's a bandwidth limitation in this case.
Yeah, bandwidth. When we are talking about digital circuits, we will talk in terms of delay and power consumption. So the delay increases, right? If I increase RL, so that is the trade-off. Okay, is it understood by all of you? Yeah.
Yes.
Okay. Okay. So the other option is I can increase the W by L. Right. So now this curve would go like this, right, for an increased W by L, and hence I can again achieve a better noise margin. Okay. Now can somebody say what would be the drawback of increasing W by L?
Capacitance, so the delay.
Pardon?
Capacitance and the delay.
Delay won't affect, because this is where it is going to charge. In fact, it is going to improve the this path delay, right? It will be able to discharge this. So my fall time will improve. Okay. Can we think of some other disadvantage?
I think high frequency.
The size of the MOS.
Size and area.
Yeah, size. More than size. More than size. There is some. Always think in terms of power and delay for digital circuits. Okay.
It'll increase power. It'll increase power.
Yeah. See, this is known as static power, right? To maintain it low, this transistor continuously remains on. Okay. So this is the drawback. When the input is high, continuously current is flowing from VDD to ground. Okay. So there is continuous power dissipation in these circuits. So that is the reason by increasing W by L, we have an issue with the power. Okay. So let me introduce you to one more term, which is this particular topology is known as a ratioed logic. Okay. When I say ratioed, okay, so lot of students keep confusing in get confused in the exam also. When I say ratioed, it means that VOH or VOL is dependent on the size of the transistor. Okay. So in this case, VOH is not depending on the size of the transistor, but VOL is dependent on the size of the transistor, isn't it? Right? That's what we discussed, right? VOL is dependent on the size of the transistor. Okay. So that is why we call this as ratioed. So these are the current equations. Okay.
Sir, one doubt.
Yeah, tell me.
Sir, how by increasing W by L power will increase that I...
Okay. When I give say when the input is 1 out here, right? Initially W by L is something. So I am getting say 100 micro, right? And that is making this VOL. Okay. Suppose let's assume this to be 1 volt, and this let it to be 1K. Okay. So what will be the V output? This is 100 micro, right? So 1 volt minus how much is this coming out to be? 1K into 100 point.
Yeah. Output should be 0. So around 0.9 volt.
0.9 volt, right? Okay. So that is not good. So let me put this as 9K instead of, right? Okay, 9K. So the output is 0.1 volt. Okay, now it is 0.1 volt, right? Now I increase the W by L, and instead of 100, it is going to 200, right? So now what will be the output voltage? VOL. It will be further less, right?
Because current increases.
Yeah, current has increased. So right, 9K into 200 more. So this will be further. V out will go further low. But what is the steady current which is going to flow here as power wastage? 200 into VDD. Right? Initially it was 100 into VDD. Right?
Okay.
So that.
Okay, sir.
Okay. So these are some of the current equations which you need to remember for analysis of these kind of circuits. For a small VDS, okay, K and dash W VOV VDS by L, Okay, then comes this linear region. So Kn VDS by 2 VDS by L, right? And for saturation, this is the equation. So these three equations will be applied, okay, to the MOS transistors for analysis of these kind of circuits. Okay, and also remember Kn is equal to Kn dash W by L. So please follow this notation everywhere. Okay, so certain textbooks and they call this Kn dash itself as K and all. So let's follow what is there in the standard textbooks. So Kn is K prime n by W by L. Okay, so these will be the equations. Okay, now we try to find out what will be this voltage. Okay, we are interested in finding out what would be this VOL, right? So how to compute that? So we have two equations. One is V out is equal to VDD minus IL RL. We are talking about a condition when this transistor is on, right? When we have given VDD here, okay. So VOH is a VDD. That is when we are not giving an input. Okay. Whereas for so VOH there is no issue. To complete VOL, so there are two conditions. Okay. Sorry. So this is for computation of VOH. When the transistor is off, you have VOH is equal to VDD. Since no current is flowing here, this transistor is off. So we can assume we are getting full voltage out here. Okay, so that is one condition. Now to compute a VOL, we are giving an VDD here. Okay, so input is VDD now. Now input is VDD. Now we want to compute what would be the V output. So one equation is this. IR is equal to the current through the resistance will be VDD minus V out by RL. Here V out is a variable as of now, right? Now the second equation is of the transistor. Okay, now for the transistor the output is very small. Okay, so I could have used this equation also, but I am using this equation. Okay, VOV minus VTS by. Okay, so this is what is given in your textbook. It will make a small difference, but nevertheless we are using this particular equation out here to find the current equation. So VDS from here to here, this is VO output, and this is ground, right? This is not no, VDS is not an it will be VDD minus this voltage is VOL, right? So this is VOL. So VGS is VDD. We have applied here VDD minus VTO and VOL square, right? So we are equating this current with this current equation, right? So that is what has been done. How do we get this equation? Is it clear to all of you? There are two. One, we are defining this output as VOL, which is a variable, right? VDD minus VOL divided by RL, and this is the current equation for the MOSFET, and we are equating these two current equations, right? Here VDS is VOL, okay, and we are this transistor is not in saturation when the output is high, so we are using, instead of using small VDS, we are using a linear equation out here, right? Linear equation. So say for in exam I might specify what equation you need to use if a different kind of circuit is given. So for whether it is linear or too small. Okay, but here we are taking what the approach which is given in the textbook. So these two current equations we have given. So everything is known here, right? VDD is known, RL is known. Now VOL is the thing which we need to compute. Okay, Kn is known. Okay, Kn is known. That means once we have fixed W by L, then KL will be known. So VTO is also known. So if you try to compute, this is a quadratic equation. If you try to solve, this is the equation which we get for VOL. All right. So from this equation, things are clear, right? Now, what are the parameters which affect VOL? Right. First is RL. So if you increase RL, out here, so it will increase. It should decrease VOL, right? Because it is in the denominator out here. Similarly, if you increase Kn, now Kn is W by L. So if you increase W by L, VOL will decrease, and like somebody rightly brought out, threshold voltage. So if you decrease the threshold voltage, so it will VOL also will decrease, and obviously noise margin also will decrease. But this again, this curve will this VOL will come close to zero. So decreased VTO means increased current. So we have to be clear what are the parameters which affect VOL and how do they affect. Okay, so is this clear to all of you? Okay, so these kind of yeah, tell me.
Sir, VOL is coming into play in the triode or the linear region, and VOH comes into play in the saturation region, sir.
Correct.
And sir, suppose with the VGS we are increasing the amount of VOL. Suppose some noise is there, and some amount of VOL is there, and it is such that
VIL is there.
VGS. Yes, the VIL input noise, sir.
Yeah.
And sir, it is increasing this value, the VDD minus VTH, the threshold value, sir. Then will the device attain saturation early? Will the device enter into the saturation region early if some amount of VL is increasing suddenly?
It depends. Like see in the input side you have say some noise like this, right? Within this band, actually the output won't change in that particular case, right? So we can assume it is not going to affect the next saturation. But obviously if you already have this much of noise, okay, static noise is already available, and then when you are giving the input signal, then only this after the input coming till this much, the output will start. So if you have a constant noise already available this much, your noise margin has reduced now. Available noise margin has reduced. Okay. Okay. And now, is it okay? Now, when a circuit is given, how to compute VOL? Okay, so you just have to equate the currents and try to find out. So you will get. So this is how an equation would come. This would be a quadratic equation. So it's looking very complex out here. But if you put the numerical values in early itself, then it will just look like a plain quadratic equation. Okay. Because VOL square is there, so you need to solve that to get the value of VOL, right? Okay. Now to compute VIL, here this value, okay, to compute the noise margin. So noise margin will be VIL minus 0. So how to compute in a VIL, right? So in that case, again we have the first equation, okay. This is the VDD minus Vout divided by RL, the current which is flowing through RL, and the current which is flowing through the MOSFET, because now this is the region of operation. You have very large VDS. This is close to VDD, right? So this will be in saturation in that particular case, right? So this transistor will be in saturation. So now that is the reason I am taking the saturation current equation, Kn by 2 Vin minus VTO square. This is the saturation equation, and now this is the current through the resistor. So I am equating these two currents. Now I am differentiating it with respect to Vn1s. So I get a minus 1 by RL, V out by Vin, and the square goes out here, right? So this is one equation, and here I write Vd by V out as minus 1. So I get this equation, right? 1 V in is equal, so I get one equation. So from here I can just bringing these things here, so I get VIL is equal to VTO plus 1 by Kn RL. Okay. Here also you can clearly see the effect of. So if I have higher VTO, like the threshold voltage is higher, so I will have a higher noise margin on the low side. Okay. So obviously when I say if I increase this low side noise margin, it will affect the high side noise margin adversely. Okay. So you have to be, not that you keep it you keep pushing it to the right, there will not be any adverse effect. Okay, that will affect my high side noise margin. Okay, now it is also like Kn and W and RL, it is inversely proportional. So this is the equation which we get. Okay, now just yeah, tell me.
Sir, can you please repeat why did we equate the saturation equation?
Yeah, see, initially to compute VOL, we took the linear region because VDS was very low, right? So for linear region, that is the condition, right? For saturation here, what is the condition for saturation? VDS has to be greater than Vin minus VTO. That would be the case here, right? In this particular case, because we have output close to VDD. So we have a VDS of the transistor very large in this case, isn't it? Is it okay?
Yes, sir. Yes, sir.
Yeah?
Thank you.
So that is the reason. Okay. So now from here we get an VL equation. Okay. So now if I have to compute this V out corresponding to VIL, although there is no figure of merit like that. Okay, generally we talk only about VIL, VIH and noise margin. But for academic interest, say I have to find out, okay, V out, okay, which is corresponding to VL, it will be slightly less than VDD. Okay, it will be slightly less than VDD. Then this computed value of VIL, if I put it in this equation, okay, so here V out is not known, right? Now we have found out V in. So if I put this V in, which I have computed into this equation on the top, I can get VIL as this. Okay, I hope it is understood till here. Okay. Now similarly, if I have to find an VIH, okay, VIH, and now again I am taking the current to be in the linear region. Okay, why am I taking the current in the linear region? Because I am talking about VOH, where VDS is very, very low. Okay, now the transistor is not in saturation region, and hence I have taken a linear equation here. So I have put a linear, this is current equation of the resistor remains like that, V out, and I have taken a linear equation. Now I differentiate both sides with respect to V in, right, and then V out by V in I write -1, right. Now if you see in this particular equation, there are two variables. Okay, one is VIH and there is another equation V out, both is not known, right. In the previous case, when I differentiated, there was only one variable, so I got VIL. So here when I am differentiating, even this V out is not known to me as of now. So I have two variables out here, one variable here and the second variable out here. So I get one equation from here, right. And if you see the topmost equation, here also V out is variable and V in is variable. So I get one more equation here. So I have one equation out here and I have the second equation out here. So I do a simultaneous equation solving thing, and with that I will come to know VIH as well as V out. Is it okay? What is the procedure to be adopted to find out VIH? All of you, right? First I write the current equation. I get one equation. I differentiate the V out by V in, and I apply that condition. D out by Dn is -1, right? And then I put that, I remove this term and put -1. I get the second equation, and I solve these two equations. So I will get the value of VIH. Okay, so this is about the resistive inverter load. Okay, so this is how the CMOS family started. Now if you see here, if I keep increasing K and RL, VOH will keep decreasing, right. The slope keeps increasing. Okay, only thing is the power consumption will increase. So this is the one what happens. Okay, now if you see here, the slope increases because of the gain, right. If you differentiate the output with respect to the current, okay, so you will have a Kn in the numerator and that is the reason the slope increases out here. So this is the slope which you need to understand what happens with increasing in value of Kn and RL. Okay. Now initially it started off like that, but after that there were some processors which were based on only on nMOS. Okay. So not that these are all just theoretical circuits. As of now we use PMOS, but the family of microprocessors based on these kind of logic also existed, okay, some time back. So that is the reason. So there are two ways of connecting these nMOS. Okay, this is only nMOS inverters. These are known as. So you have an enhancement load. So either you can connect here like this, right? Or you could go and separate an VGG out here, right? So both has got its own advantage and disadvantage. If you connect a VDD out here, okay, the gate is given high. The maximum output voltage can go is like we have seen for nMOS. It is not a good transmitter of 1, right? So maximum output will be what? It will be VDD minus VT, right? If you connect in this particular configuration, so relatively simple fabrication process. Or the second option is you give a separate VGG which is more than a VDD. Okay, it should be VDD plus VTN at least. Okay, at least it should be VDD plus VTN, right? In that case, this output can go up to VDD, right? So this is the second configuration. But the problem here is you require two power supplies for these kind of systems. Okay, so that is an issue out here. So you should have two power rails, one power rail higher than the other. So this is enhancement load and MOSFET inverters. Okay, this also has a drawback of high static power. Okay, is it okay for all of you? Okay, so instead of enhancement mode, we can also have an depletion nMOS load. Okay, so here since the VTH is negative, I will get a full VDD, right? So even though it is nMOS, okay, I can get full VDD because VTH is negative. So I get an VTH is and I can use a single power supply also. That's not an issue. But then these are all enhancement type MOSFETs. This is depletion type MOSFET. So it will require one additional process, okay, for during fabrication. Circuit topology wise things appears to be simple, but then to make an depletion MOSFET, like when we learned about CMOS process, we learned those 6 different masks are there for an nMOS and PMOS. But if you, they are all enhancement type nMOS and PMOS. But if you are considering now depletion type devices also, then the number of masks, so the number of processing steps also increases. So that is the reason with the depletion load nMOS inverters.
Sir.
Yeah, tell me.
Sir, in the previous slide, one more back.
Yeah.
So here I didn't get why here minus VT is there, VDD minus VT for VOH level.
Yeah, we talked about when we have an nMOS, it cannot transmit a perfect 1, right? Now if I take an example out here, right, when the VDD reaches VDD minus VTN, right, what would be the gate to source voltage now?
Gate to source voltage.
Okay, gate is VDD.
It has to be VTN.
And source will be VDD minus VTN, right? So if you subtract it, it will come VTN, right?
Correct.
Right? It cannot go beyond that because this transistor will get switched off in that particular case.
Okay.
Right? So that is the reason, right? Okay. In this case, what we are doing, we are giving VDD plus VTN as gate. Okay? So in that case, it will be VDD plus VTN minus VTN. Okay, so you will get VTN there in the VDD there, right?
Okay.
So if you give say, so let me ask you something. If I give 2 VDD plus VTN, what will be the output voltage?
2 VDD. No, output will not be 2 VDD.
It will be VDD only.
VDD only.
It will be VDD only. Okay. So because this is the potential from here, right? So it will be VDD. So this is the minimum voltage what we need to give is VDD plus VTN. Okay. So in this case, the VTN is negative, right? So if it is negative, it is VDD minus this will be V out will be whatever is negative. So it doesn't matter, right? So here it is positive, that is why it is an issue. If VTN is negative, I will still get VDD. Okay, so with depletion. Okay. Because even if it is 0, it can conduct. Okay, it requires a negative voltage for this to be switched off. So since VT is negative, it will continue charging it till VDD. And that is okay. Now we say for the depletion, like this was also used. Okay, so this family of I think the initial, if I remember, 386 processors were only nMOS processors. Okay, they were based on this family. Okay, where they had depletion. PMOS was not yet implemented in those days. So it was this particular combination was used for 386 processors. Okay. Now if you see here, now it is K driver by K load. Okay. So this is the curve you will get. Okay. KR is nothing but K driver by K load. Okay. K driver means if you can see that. Okay. If this is stronger, W by L is stronger. Okay. It will keep moving toward. It will get switched faster. Okay. So it will keep moving like this. Is this clear? So this derivation is also there in your textbook where you are equating these two currents. Okay, so so please go through the derivations of this topology as well as this topology. I have given the derivation only for the resistive load. Similarly, you can find out VIL noise margin for these topologies also. Okay, so you so those equations are given. The technique is same. Okay. So the final outcome will be this. Okay, you have to understand, if you increase the, if you make nMOS stronger, the VTC curve will move towards the if you make the pull down network stronger, it is going to pull this curve towards the left. Okay, so this is depletion load nMOS, right?
Sir,
yeah, tell me.
Sir, the characteristic curve between V out and V in for PMOS like current source will be the same as RL, or it will be different?
It will be different. We are going to see that now.
Okay.
So this is the CMOS characteristics curve, where I have, instead of resistance, I have a PMOS out here, right? So if you see here, what happens is when V in is equal to high, this transistor is switched off, and I just have a channel resistance here. So whatever is the output that gets connected to the ground, so there will be an effective R through which the capacitance get discharged completely. So I have V in OL is equal to 0. Similarly, when the V in is 0, this will be off and this will be on. So the output will be fully charged to VDD. So irrespective of the size of these transistors, okay, the output will be charged to VOL or it will be charged to VOH, right? So it is not so is it ratioed, or is it going to be ratioless? It will be called
Ratioless.
so it is ratioless. Okay, so all these are ratioed actually, because this VOL is dependent on the size of the transistors. Okay, in this particular, when I am using an CMOS inverter, VOL is 0, VOH is 0. So this is the only topology which is ratioless. Okay, so here, so this is what how it works, right? Like, so there are certain important properties of CMOS. One is it is rail to rail output, ratio less, right? And in steady state, there always exists a path, finite resistance between the output to VDD and ground. That it means here, this is the output node. This is not floating at any time. Okay, it will be either be connected to VDD or it will be connected to ground through some circuit. Okay, so that is not the case when we are going to study about pass transistor logic, or when we are talking about dynamic logic. We will see that that is not the case. Okay, sometimes this nodes is floating. Okay, when I say static CMOS design, in that particular case, it will be either be connected to VDD or to ground. Okay, so the input resistance of CMOS inverter is extremely high. So steady state current, there is no input current required. So to drive this inverter, there is no input current. Okay, similarly, there is no direct path between supply and ground, only under steady state operating conditions. Okay. That means only during transient operation there is a supply path between VDD and ground. Otherwise there is no path. One of the switch is always open, so there is no steady state current. But in all these topologies, okay, all these topologies we studied here, there was a constant current dissipation from VDD to ground. Okay, including in all the BJT based circuits also, there is constant power supply path between VDD and ground. It is only after PMOS was fabricated and we have CMOS topology that there is no direct path between supply and ground. Okay, so this is there only for CMOS. Okay, and now there is another important thing. This is another very important aspect of CMOS. Okay, an inverter can theoretically drive infinite number of gates. Okay, so there is no restriction on fan out, because if you keep increasing the number of transistors at the output, okay, still VOH will remain VOH, that is VDD, and VOL will remain VOL, which is 0. Okay, so though that is not going to change. Only thing which will happen is if you keep increasing fan out, the propagation delay will increase and the dynamic power will increase, because now a larger capacitor needs to be charged and discharged. Okay, so the dynamic power will increase as you increase fan out, but the noise margin and will remain the same, and the static power will continue to be 0. Is this properties understood by all of you? Is it okay? Is there any doubt in any of these points? No?
The problem is the ratioless property that we have. So we define if the circuit is ratio or ratioless only on the basis of VOH and VOL.
Yeah, correct.
We don't see the drive strength of VIL and VIH, right? Only
Nothing,
VOL
nothing.
and VO.
Yes, if the output VOL or VOH, it is a function of the size of the transistors, then we call that it is ratioed. Okay.
Okay, so all other aspects are equal.
Yeah. Shall we start? Yeah, I guess Lijos. Yeah, tell me.
And then actually till now whatever the CMOS characteristics we saw, like only the PMOS was on, correct me sir? nMOS was off.
Yeah.
അല്ല നമുക്ക് ഇനി ഇവിടെ എന്തെങ്കിലും പണിയാണെന്ന് വിചാരിച്ച്
somebody call up
സ്ഥലം എടുക്കണ്ട അവിടെ ഒന്നും
Lijo
ചെയ്യണ്ട.
and ask him to mute his mic.
അല്ല അതാ പറഞ്ഞ അപ്പൊ ഇവിടെ എന്തെങ്കിലും ചെയ്യാമെന്ന് വിചാരിച്ച് ഇങ്ങോട്ട് സ്ഥലം എടുക്കാതിരിക്കും. അതിനകത്ത് ഒതുക്കണ്ട. മേലോട്ട് സ്റ്റെപ്പ് എന്ന് പറഞ്ഞാൽ മേലോട്ട് നമ്മൾ എന്തെങ്കിലും ചെയ്താലും കയറാനുള്ള
Sir, you can mute yourself, sir. Mute all the participants. You can.
Yeah, I can do that.
Yes sir, you can mute people.
Yeah, let me try that.
Now Lijo is in mute already.
Yeah, okay, he's gone. Okay. So yeah, somebody had a doubt. Can you repeat that? Till now we have been learning only about nMOS switching. We are going to learn about PMOS switching now.
Okay.
Okay. Yeah. Okay. So now I have this particular circuit. in which I have an nMOS and I have an PMOS also. So let's first try and make the load line for PMOS. Okay. So with respect to the V out. Okay. So this is like an IDP for PMOS will be negative, right? Because it is I source, current is coming from source to drain. So this is a negative. Okay. And VGS is also negative. So that is why this curve is going here in the bottom. Okay. 0 will be here, -1, -2.5. It is increasing for VGS. So this curve is for a PMOS. If I draw it, it will like this is ID is plotted. That is why it is negative out here. And now if I try to plot the current like this itself, so I can invert it. So this will go onto the top, right? Now if you see here, for V in is equal to 0, VGS is going to be the maximum here. So this VGS is equal to 0 line, and V in is equal to 0 line corresponds to this particular curve, right? For V in is equal to 0, only then VGS will be maximum. As you keep increasing V in, right, then this VGS will be lesser. So that is why this has got transferred. Now also this output is actually VDD minus V out. So here if I put V out here, okay, these curves will look like this now, right? Because now this is the PMOS load line, right? So what does PMOS load line indicate? When V out is equal to VDD, right, the current will be 0, because this is 0, right? VDS is equal to 0 in that particular case. And as the V out reduces, then you have the currents going high. Okay, currents is going high. So and also for V in is equal to 0, this is the top curve, the topmost curve. And as V in increases, this curve comes down. So the PMOS curve is like this. So if you superimpose both these curves, okay, it will look like this. Okay, so these are the green lines indicate the nMOS curves, and the orange line indicates the PMOS curves. So the various operating conditions for various V in. Okay, so so for example, when V in is equal to 0. Okay, so this is the bottommost line is the one is for the nMOS. For the PMOS, it will be the topmost line. So they will interact here. So as V in will and if you see here, as V in is increasing, this green line will keep increasing, and these lines will keep decreasing. So the intersection points will get different intersection points. So if you plot all those intersection points, so initially when nMOS is off, PMOS is off, nMOS okay, will act as a small resistance, okay, or it will be in the linear region. Then slowly as the V in increases, okay, then still it will be PMOS will be saturation, and then it will be in resistance. When both at somewhere in between, okay, when VD and V out is somewhere half of VDD, both the transistors will be in saturation. And as the input voltage increases, nMOS will become off, okay, and then PMOS will go into the linear region. Okay, so nMOS will start with linear, it will come to saturation, and then it will go to off. PMOS will initially be off, then it will come into saturation, and it will go into a linear region. So this is the curve which we get. So this is the load line which we get. Okay, so you will find VOH. This is for a 2.5 volt system. So you have a VOH as 2.5 and VOL as 0. Okay, so this is initially nMOS is off and PMOS is in the linear region. Linear region is also called as a resistive region, and then you have this where it is taking a -1 slope, and then it is coming here. Then again you have a -1 slope out here, and then it is going here. And here is nMOS is off completely. PMOS is completely off. Here nMOS is completely off. So there is no static currents at both these points. Okay, and then we define something known as inverter switching. Okay, that is if you draw an curve like this at 45-degree slope, wherever it intersects this curve, that is known as the inverter threshold. Okay, so this is at this particular inverter threshold, V in is equal to V out. Okay, so is it is the inverter threshold definition understood? I think there's one more slide on it also. Otherwise, is the VTC curve okay with all of you till here?
Sir.
Yeah. And the region of operation also.
Sir, when
yeah, one of you.
Sir, when nMOS is off,
okay,
and PMOS is on, that is in the linear region, operating in the linear region.
Yes.
So the output will be VDD, sir?
Yeah, it will be VDD because there is no constant current flowing. Initially, this node may not be at VDD, so it will get charged till VDD. So since it is an nMOS, it can pass a perfect one. This output will come up to VDD. Similarly, when I am when the Vin is high, this is a perfect zero transmitter, so it will pull down all the voltage to zero. Okay.
Okay. Then, sir, when we have started increasing the Vin, then the nMOS the current IDS start flowing through VDD.
Correct.
Then Vout will start reducing, sir, and so it is a slight slope, sir, in the second phase of the curve from 0.5 to 1.
Here. Yeah.
Vout will reduce, sir.
Yeah, that is because this will start pulling the node voltage down. That is the reason. Right? Initially what happens is this is switched on, right? Okay, whereas this is trying to charge the node, this is trying to discharge the node, but obviously you are giving a small Vin, so this will not be able to pull the charge to zero. It will not have adequate current carrying capacity to pull it down because of lesser overdrive voltage. As you keep increasing the input voltage, it will come to a state where this is able to pull more current than this, okay, because simultaneously the overdrive of voltage of the PMOS is being reduced and the overdrive voltage of the nMOS is being increased. So finally we will come to a state where this is not able to give any current, this is able to pull all the current, and hence the voltage drops and it goes to zero. Is it okay?
Yes, sir.
Okay. Yeah, Jennifer, you had some doubt?
Yes, sir. Like on the previous slide.
Okay.
Still previous slide.
Yeah.
Still more, sir. Sir, can you explain this first two curves? Actually, I didn't understand this. IDP versus VDD.
This is just the PMOS characteristics. Okay, gate source characteristics. This is negative. As you keep increasing negative, PMOS currents increase, right? Because this is gate source. Source gate has to increase, right? So gate source means it will be in the negative direction. Is it okay? And I source will increase. I drain is negative, right? For a PMOS, the top one is source, bottom one is the drain. So in this case, I am plotting I drain, and hence it is in the negative side. Okay. Now instead of IDP, I am writing IDN. Okay, the current here, right? So and that is why this is negative. I have pushed it on to the top, just to overlap these two curves and see the operating points. Instead of IDP, I am plotting IDN. IDN is nothing but ID source. So that is ID source of the PMOS. That is why this has gone on to the top. Okay. Okay. Right. Okay. Now the switching threshold of an inverter. This is an important parameter. It is where Vin is equal to Vout. Okay. Graphically at the intersection of the VTC curve where Vin is equal to Vout. At 45 degree slope, I make a line. It will intersect here. So this will be known as threshold, inverter switching threshold. Okay. So roughly speaking, if the voltage is below this, I assume as 0. If it is above this, it is just switching from one state to other. Okay. But obviously you can't give an input voltage slightly below. You have to take care of the noise margins. Okay. If it is to work properly, you have to ensure that it is lesser than VIL and greater than VIH. Okay, so so this is just a parameter which gives us switching threshold. Now to find out what would be the switching threshold of an MOSFET. Okay, so this is the equation of an MOSFET, where this channel length modulation also has been written here, but I'll neglect that. Okay, then when this V out is VDS by 2, okay, both the transistors will be in saturation. So I am equating these two currents out here, right? So channel length modulation has been, so ID is equal to Kn by 2 VGSN minus VTN square, Kp by 2 SGP minus VTP, okay, square, right, for the PMOS. Now for the PMOS, the gate to source voltage will be VDD minus Vin, right? VDD minus Vin. This is the voltage which is available out here. VDD minus Vin, right? And for threshold voltage, we are taking Vin is equal to V out. Okay. So so this is VGS minus VTN will be VM minus VTN, and this will be VDD minus VTN. Okay. So if I substitute in both these equations, okay, VGSN is equal to VM and VSGP is VDD minus VM. So I get the equation for VM like this. Is this okay to all of you? What I have equated the PMOS current and the nMOS current. For the nMOS, VGS is VM, because I am trying to find out the inverter switching threshold. And what is switching threshold? Vin is equal to V out. Okay, somewhere in the mid. This is the curve. Vin is equal to V out. So Vin is VM. Like for the PMOS, this is Vin and this is VDD. Okay, so this is VM and VDD. So VDD minus VM, VDD minus VM. So I put here VDD minus VM. Here I write just VM minus VTN. Okay, and equating these two equations, and I get this equation. Okay, for VM. Okay, now from this equation, is this okay with all of you? Okay, it's a simple one step equation. You can just have a look at this. Okay, now I define something known as an R, which is a root of Kp by Kn. Okay, because I have a Kp here, I have an Kn out here, right? I have Kp Kn. So I am defining R as Kp by Kn here, right? Now this is the VM equation. Now if I see this VDM equation, okay, now for a symmetric switching, okay, for this VTC curve to be symmetric somewhere between VDD by 2, if this has to be in VDD by 2, then I can say the noise margin on the low side and the high side will be equal. This is known, and the rise time and the fall time will be same. So I will prefer to have a symmetric VTC curve, and for that, in this equation I require VM as VDD by 2, and to achieve that, two conditions should be met. Okay, first VTN and VTP should be the same, and that is generally the same for any technology. For most of the technologies, VTN and VTP will be kept same, okay, by the lab. But R is a design parameter, okay, because R is what? Kn by Kp. That is if you see here, this has to be same for R equal to 1. This is the condition to be met. Okay, but mu n and mu p are not the same, right? So you will find from this equation, if R needs to be 1, I have to keep W by n by W by p is equal to mu p by mu n. Right, and mu p is generally 230, whereas mu n is around 480. So I will have to keep the PMOS, okay, 2.5 times the width of the if L is also, generally we keep L the minimum, so width of the PMOS is generally kept 2 times the width of the nMOS. Is this thing okay to all of you? Right, if I go to these two transistors, the mobility of the PMOS is actually 2.5 times the, if I consider this as a potentiometer, both the resistances should be the same, right? For so then only I will get VDD by 2, right? And now the mobility of PMOS is 2.5 times lower than that of the nMOS, and to compensate that, the width of the transistor I will keep 2.5 times, so that they become equal current carrying capacity transistors to get a symmetrical. So because of the mobility issue, okay, the width of the nMOS is generally PMOS is generally kept 2.5 times bigger than the nMOS. Is this thing clear to all of you? Is it okay? Okay, let me move ahead from there. Okay, now if you see here, now if I KR I have defined as Kn by Kp. If I increase KR, that means I am making an N transistor stronger. That means I am not keeping this in a ratio 2.5. If I keep an KR, for KR to be 1, I have to keep 2.5 times width. Okay, because K includes the mu also, right? So if I keep if I keep the nMOS stronger, this VTC curve will move towards the left. And if I keep PMOS stronger, then this will move towards the right. Okay. If I keep PMOS at 2.5 times that of nMOS, I will get KR is equal to 1, and I will get this curve which is there exactly in between 1. Is this okay with all of you? But here if you see, as compared to the previous states, okay, whatever is we are doing, we are changing the width of the transistors only to move the VM, but otherwise the VOH and VOL they remain VDD and 0. Is it okay with all of you now? Okay, so I have put only for static characteristics itself one full class, because these are very, very important aspects you need to. So I am stressing this, and in case you have doubt, please ask me. Yeah, tell me. Yeah, Gajendra.
So you are increasing K.
Increasing the?
Sir, if you are increasing the KR, that means we are increasing the doping level of the P-type P-MOSFET, and therefore the BTP of the MOSFET is also increasing, as a result of which the curve is going to the left.
No. See, we are talking in terms of a circuit designer. We don't have control over threshold voltage, doping, and nothing. Okay, the only parameter which we can change as circuit designer is W by L ratio. Okay, so when I am saying I am increasing KR, I am increasing Kn. And what is Kn? If I go back to the current equation, here, Kn is W by L. So the Kn dash parameter is not a design variable for the circuit designers. I just have W by L. So I am increasing W. Is it okay?
Yes.
Right? Okay. So for example, if I keep this 400 nanometer, right, and 1000 nanometer PMOS, I will get width. Okay, length being 180 for both, I will get this curve. Okay. Now if I increase the value of N, or I decrease the value of P, okay, either way I will move towards the left. Okay, and I will move towards the right if I decrease the value of N or increase the value of P. Is it okay?
Yes.
Okay. Now for short channel devices, okay, the current equation here, this is the equation which we used, right? So that equation gets modified with the VD saturation equation. Okay, so this equations take care the saturation also. So if I do the substitutions, okay, then I will get an Vsat. Okay, R is equal to Vsat by Vsat P divided by Vsat N. Instead of mu, now I get Vsat. Now Vsat of an electron is 8 into 10 to the power of 6, and Vsat of an PMOS is 6 into 10 to the power of 6. Okay. So for very, very short channel, like if you see when I talk about 45 nanometer, 22 nanometer and all, so there you will see that you don't have to keep PMOS, okay, twice the size of the nMOS. Okay, even if you keep equal, or if you keep just 1.5 times also, it is not good enough. Okay, so when I am talking about the short channel devices, okay, mobility is not the constraint, but the saturation velocity is a constraint, and the saturation velocity of the PMOS and the nMOS are very close to each other, and hence I don't have to really keep the PMOS 2.5 times that of nMOS. I can keep it close to each other, right? But for a 180 nanometer technology and all, for all our designs which we are going to do in LT Spice, you have to keep PMOS 2.5 times. Okay, even that 2.5 times will get modified in the next slide. Okay, let me show you that. So this is like for a short channel device. If you see here, if nMOS and PMOS size are kept almost 1 also, you are getting a symmetrical curve. Okay, that is because the saturation velocity of electrons and holes are almost same. So that is the reason you are getting close to 1 out here, right? Now this is WP by WN. Okay, now if I am keeping WP by WN, okay, for a 2.4 volt system, if I am keeping the PMOS width as 2.5 times that of nMOS, I am getting an inverter threshold of 1.18. Okay, if I am keeping it 3, right, it will move towards the right, so it will get 1.22. If I am keeping it 2, it will move towards the left. I am getting 1.13, right? Now if you see from 2 to 2.5, okay, it is not making much of a difference. So I use a simple rule that the nMOS PMOS width will always be kept twice that of nMOS for symmetrical VTC. Is it okay with all of you? Ideally, from the theoretical expression, I should keep 2.5 times. Okay, but practical observation is that when I am changing it from 2.5 to 2, right, so it is making marginal difference only. It is, although it is making a difference, but then the rule of the game out here for CMOS design will be, for long channel devices, the width of the PMOS will be twice as that of the nMOS. Okay, so this is the golden rule which we are going to follow for all our design in the classes in the future also. Okay, so where did that 2 come? That we have learnt today. Okay, so we are going to use PMOS width twice. Okay, so that will keep the VTC curve symmetrical. Also, it will keep the rise time and the fall time same. Okay, because if you keep both same, PMOS will have a lesser current, so it will take that much more. So your rise time will increase. Okay, so if you keep PMOS twice the width of the nMOS, then your rise time and the fall time will be the same. Okay, so that is about. This is a noise margin. Okay, this is just an approximation of the curve. Okay, here actually the slope will be -1. Okay, so now to find out an VIL of a PMOS. Yeah, tell me.
So just one question on slide 25. There, sir, we saw so the system VDD is 2.5. So for symmetric, VM should be somewhere around 1.25.
Yeah.
And even for a factor of 3, we are not able to achieve 1.25. Is it because of some other parameters like channel length modulation, something which you have not considered?
Yeah. Correct. Or correct. It is because of that. Right? Because of that. Right. Now to compute a VIL, okay, what do we do? Right. So again, we take this for VIL. This is the equation, right? So this is for the nMOS. It will be in saturation. For PMOS, it will be in the linear region. Okay. So you are going to equate the linear region and the saturation region of the nMOS and linear region of the PMOS. So you consider this equation, right? So that is one, and then you differentiate it and you put V out by V in, and put a value of -1 there, right? So you differentiate it and you put -1 here, so you get the equation of VIL. So you get this particular equation, right? So this is the standard procedure of computing VIL. You write the equation of PMOS. This is the nMOS equation. This is the PMOS equation. So the region of operation should be clear. For VIL, this will be in linear region PMOS, and nMOS will be in saturation region. Okay. Once having written those two equations, you equate those two equations, differentiate it with respect to V in, and you write D out by dV in is equal to -1, and you come and you find out the value of VIL. Okay, so you get a VIL out here, right? Similarly for VIH, now this will be the nMOS will be in this will be in saturation, and this will and the nMOS will be in the linear region. So this gets swapped. Again, you differentiate it, and you can put it in a V out by D1 is equal to -1. So again you get VIH value. Okay, in all these equations you might have to solve do a simultaneous equation. One is by differentiating it, and by the second is by directly putting in this equation these two values. Okay, so all of them will give values of VIH and VOL. Okay, so these are the noise margins equations. After having found out VIL and VIH, okay, noise margin low will be VIH -0, noise margin high will be VDD minus VIH. So please go through all these equations in your textbooks. These are all important derivations and important numericals for your exam also. Okay, so I hope these things are understood till now. And now talking about static loss. Okay, we know that the current will flow when it is even though it is on, there will be some path between VDD and ground, and hence that is known as static. And why is that static current has become a big issue is because as we keep increasing, we are decreasing VDD because of technology. We need to decrease the VDD, VTH also, right? To keep the ID at reasonable levels, because unless you keep ID at reasonable levels, otherwise you will have greater propagation delay. So with technology, VTH is decreasing, VDD is also decreasing, and you are decreasing both VDD and VTH to keep ID constant, and because and VDD is being decreased because to keep the electric fields constant. Now since both VDD and VT are reducing, right, and VTH is reducing, VTH reduction results in a higher leakage current. Okay, so this is to be kept in mind, and this is the current. This is the plot which this is for 45 nanometer. This is W. This is 2W. So I get an symmetrical, like around. I can get an switching at around 0.5 volt. Right. If I keep this as 2W, this is at W. So if I keep that, I'll get a symmetrical curve. This is 15 pico ampere is the leakage current. That is because of the nMOS. 3.5 is the leakage current because of the PMOS, and both are switching. I get this particular when both are on. Okay, in between I'll get high currents. Okay, between VDD and ground. So this is known as the static loss VTC curve. Okay. Now to reduce the static current, you can go through this particular paper. It says for submicron devices, if you keep width low, okay, that will reduce VT. Okay, and reduction in VT will increase the static current. So it says if you want to reduce static current, you have to increase the width. Okay, that is what it says. But if you increase the width, the capacitance increase, so that might deteriorate your switching characteristics. So but if you are designing a circuit which is going to remain ideal for long time, in that case you might want to consider using large width transistors. Okay, but otherwise that is not recommended, because it will large width transistors will result in high dynamic currents. Okay, so this is about static loss. Okay, there are several
sir, one doubt.
Yeah, tell me.
Sir, what is the reason of static current?
Static current is because even if you are not applying gate voltage, because the threshold voltage is very low, because of at room temperatures there will be some minority carriers, and now since the threshold voltage is very less, you don't have very strong reverse biased PN junction between the source and the drain and the channel region. Okay, we saw that initially in our first class. There will be a diode which will be reverse biased. So now it is not, because we have to reduce the threshold voltage. So now that diode has become very weak diode. So, and because of thermal emissions, there will be a small current which will flow. Okay, it will be in picoamperes, but since we have billions of transistors in a core, so if you multiply this picoampere by billions of transistors, then it will come to a significant current, right? So that is the issue. Okay. Yeah, somebody else also had some doubt.
Sir, how VT will improve with respect to width increase? That one I am not able to understand.
Here. Okay.
Yes, sir. Because while if you see, right, we increase width means there will be more leakage will be there, right? So how it will improve VT? I am not able.
Okay. So there is an physics behind it. I have referred that paper out here. Okay. Generally, that is the specific reason why I have put this slide, because it will appear to us that if you keep width low, more resistance, lesser current, right? Okay, so but that doesn't happen in a short channel. That is true for a long channel. Okay, even for 180 nanometer, if you reduce the width, you will find little bit of current is reducing. But when I am talking about 45 nanometer and 25 nanometer, okay, if I reduce the width, it affects my VT. Okay, so please have a look at this paper. Okay.
Oh, okay.
Okay. Yeah. Somebody else. Yes, Jennifer, you had.
Sir, you were talking about that static current, no?
Yeah.
Like that we can call as leakage current also, right? In that case?
Okay. Now, actually, I should be calling it as an. This is in for CMOS topology. Okay, static current means when the input is not changing. Okay, for a CMOS, the static current is leakage current. Okay, for a CMOS, static current is known as the leakage current. Okay. Here, static current is not leakage current. Or let me take a simpler. Here, the static current is not leakage current. Is it understood or is it confusing?
Oh, okay, sir. When
V in is equal to 1, right? There is a static current, right? That is not leakage current.
Yes, yes.
Okay, that is the on current of this transistor. By design, the on current is static current here in this particular circuit. Okay. Okay. Anyway.
But when you explain the CMOS, that is leakage current. Static current is not.
But leakage current. So circuit to circuit, static current by definition is when the input is static. Okay. For here it is not leakage current. So I never spoke about leakage current in this. Okay. Very good. You brought this point. It should be clear to all of you. Static current means when the input is not changing. In this particular circuit, there is high static current. Okay. And that static current is not leakage current, but it is on current by design. To bring this voltage to 0, I am purposefully taking some current from VDD and dropping across R. Okay, so that is not leakage current. Okay, whereas in CMOS inverters, generally there is no static current ideally, because one of them will be off, but practically static current is leakage current. Okay, and that is why it is very less. Okay, so for CMOS current, theoretically static loss should be less, but because of leakage there is small amount of static current. Is it clear to all of you now? What is the yeah, okay, thanks a lot. Okay, so that is reducing static. Now if you have most of the processors these days, okay, they employ this, okay, multiple VDD. You have one more module which keeps sensing which part of the circuit is not being used. So in those paths, okay, the power is reduced. Okay, and also okay, that is a different that is known as dynamic scaling. This is different. Here what is done is, if you see here, this is the critical path. Okay, this is the critical path. Okay, longest time. So 10 nanosecond. This path is non-critical, because even if the data comes at 5 seconds, I have to wait till 10 nanosecond here. So the clock will be set as per 10 nanosecond clock only. What I can do is I can decrease the VDD in this particular path to reduce the static loss. Okay, so that is also done in VLSI circuits. Okay, and also here also. So if I reduce VDD,
if you reduce the VDD in the second one, won't it cause the hold violation, because second one is critical for the hold analysis?
No, we will not talk about hold violations out here. Okay, because if you see here, this is like the next clock. The clock is set as per 10 nanosecond. So this was reaching here at 5 nanosecond. So I can wait for the. I am talking about setup time of these two flip flops. So the input is coming here at 10 nanosecond. So my clock will be at least 1 by 10 nanosecond, because I can't have a faster clock. So I have to wait. Here it was reaching at 5. So in this particular path, I reduce the VDD now. And hence if I reduce the VDD, it will come delayed, but still it is faster than the 10. So I can save some amount of power. Okay, is it okay with all of you? Right? Okay. So these are the kind of things which is actually employed in processors. Okay, in these designs, because now although this is targeting static power only. Okay, to reduce, but then we initially think it is in picoampere, so we don't have to worry. But you also have to think in terms of number of transistors. So there are billions of transistors, right? So this picoamperes into few thousands also will take it into nano. So that is the reason you have to take care of these issues also. So this is one way of doing it. The other, so in multi-VDD design, okay, additional VDD requires to be created by DC to DC converter, area overhead, level shifters will be required, multiple routing. But in spite of all these things, it is being done in modern day processors, okay, because power is a major issue. Okay. Now also what we can do is, in the non-critical path, we can increase VT. We can use high VT devices. Okay, so that now this by increasing high VT also we can reduce the static leakage. Okay, so that is one path. Even this is employed in most of the modern day processors, where in non-critical path we use high T devices to reduce the static leakage. Correct. Okay, when you are designing circuits and if you want to bring down the overall power consumption, this option is also available with you. Like most of the technology offers high VT devices, low VT devices and normal VT devices. Okay, if you are working in cadence, say 45 nanometer, when you are taking from the library, you will have 3 types of nMOS available there. Okay, normal VT nMOS, high VT nMOS. So in the circuit you can use a mix and match of high VT, low VT devices depending on the circuit which you are designing. Okay, so these kind of techniques can be employed. Okay,
so sir, in this case, multiple VDD is not required.
Multiple VDD. Yes.
The only VDD which is given to the above path, the similar we can give here.
Yeah, correct. Only thing is, once this, see the problem out here is, once you fabricate it, nothing can be done about this particular circuit. Okay, this will continue to remain slow. Right, so in those kind of circuits, you can do that. But say for example, you have something known as dynamic scaling in some portions of the circuits when and when it is not being used. Okay, you can reduce the VDD. That is known as dynamic scaling. Okay, that's what your laptops handle, which are with those modules which are not used when it is going to sleep, or some modules will be shut down automatically by reducing the VDD. Okay, so that is known as dynamic voltage scaling. So here you have a flexibility, right? You can control the VDD. Here it gets fabricated, then nothing can be done about it. Okay, so these are some of the pros and cons. Okay, but then many modules within modules, if you have some path, this doesn't get changed at all. This entire module is fixed. Then obviously you can use VTH also, high VT devices also. So these kind of. So the challenges will be additional mask and design library has to be made. Okay, high VT. So these things are already done. So we do use multi-VTH design also, but these are some challenges. Okay, so with that we come to an end of the theoretical thing. So let me just show you some simulations before we. Okay, so this is like, you have an R, and then you have a CMOS. So I am doing an VTC curve. So let me just, so you see here, so this is the for where, if I view step legend. Okay, so the green one is for 25K. As I keep increasing R, I find it is become sharper, and VOL is going low. Okay, so is it okay, VTC curve? I am using increased R. Okay, so I am getting better curves, VTC curve here. But like we discussed in the theory class, I can get this better VOL and better sharper curve by increasing RL, but the drawback will be the higher propagation delays. Okay, because if I increase the value of R, then the propagation delay will increase. Okay, so this is the kind of curves which we get, VTC curves for
because of decreasing current, right sir? Propagation delay.
Yeah, because R is large, so if this node requires to be charged, it will be R and C will come in series. So increased R means propagation delay will increase. Okay, but better VTC curve we get, and you see here. Okay, the lower VOL, OL is slowly going lower and lower. Okay, now like we talked about, if I plot the currents also, if you see here, okay, since I have taken two this thing, so the legend is not available. Okay, for R is equal to 25, this is the current, and R is equal to 100, this is the current. So you see the static current is now in 70 micro here. Okay, when V in is equal to high. For R is equal to 100K, it is only 14 micro. So the static current also increases, right? If I reduce R, okay, the static current also increases. Okay, so propagation delay and power, okay, there is always an trade-off. Okay, so these are the various design issues which you should know. Okay, what happens to the propagation delay, what happens to the static power, so all these things you need to know. Let me show some more simulations. Okay. So this is like now what I have done is, this I have kept 400. Okay, PMOS I have put it as a WP. Okay, I have kept it as a variable. Initially I am using 1:1, then I am increasing it to 1200, that is 3 times, and then 800, and then 1200. Okay, 400, 800 and 1200. So that is the width I am increasing out here. Right, okay, so okay, so for 400 I am getting this curve. Now I have increased the PMOS here, so I am getting it has moved towards the right, and I have increased it further, it has moved again towards the right. Okay, is it okay with all of you? How this curve is, VTC curve is moving towards the right. I am keeping the nMOS width constant, 1:1 if I keep. Okay, I am getting, even this is 1.8 volt, I am getting less than 0.8 volt here, although I am keeping nMOS and PMOS width as same, because the mobility of the PMOS is less. So I have to increase the size of the in this particular case, if you see here, for the 180 nanometer technology what we are using, even if I use 1:2, it is coming around, the switching is happening around close to 0.8. So if I have to get a symmetrical swing, right, so it is coming close to 2.5 value. Okay, 2.5 to 3. Okay, but we will take for all our designs, for all our assignments and designs, we will take VTC to be WN is to the WP is to WNS and 2:1. Okay, for the design. For the VTC curve, you can change it and try and find out what is the best possible for symmetrical. Okay, so that ratio for this particular lab exercise, you can try and find out what would be the best size of the PMOS to get a symmetrical. That you can do.
Sir, what is the supply voltage here?
1.8 volt.
1.8.
Okay, I am using 180 nanometer. That is why I am using 1.8 volt. Okay. And then, yeah. So this is to see the currents. Okay. So see, if I am this is the current. So if you see here, initially the current is 0 out here, then it is going high, and then it is coming low. Okay, so if you have to find out the correct values and all, you can put a cursor out here, right? So that I have explained earlier also. Attach cursor first, okay, and then you move this cursor to the desired value. So a window would pop up here. So it says 48.6 micro. So that is the peak current which will flow when input is exactly at for the inverter threshold level. This is known as the inverter threshold level. Okay. So here, if you see, it is not symmetrical in this particular circuit. At 0.8 volt is the inverter threshold voltage out here, right? Because I have not used PMOS, I have given 800, and nMOS I have given 400. So 1:2, right? So and hence you have to keep it more than 2 to exactly get this thing at 0.9 volt out here, right? So this is the exercise which I gave you for your assignment. Okay. For this, the first one, since we are reading in detail about the DC characteristics, we will target and keep it at 0.9 volt, and henceforth after that, when we are going to design bigger circuits, this slide 0.1 volt offset we will not take into consideration. Okay. So I think with that I will stop it for today, and thanks a lot. If anybody has got any doubts, we have 10 minutes. I can take on those doubts. No doubts? Then analog students will meet at after 1 hour.
Thank you, sir.
Okay. Okay.
Thank you, sir.
Okay. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yeah. Thank you.